Hi, I'm Alex Fong, Vice President of Engineering at Hinalea Imaging TrueTag Technologies, and I'll be discussing our work in the detection and measurement of aflatoxin in maize, cornmeal, and other agricultural products using hyperspectral imaging. Aflatoxin is part of a family of carcinogenic toxins produced by fungi in warm and humid regions and can be found in agricultural crops such as maize or corn, peanuts, cottonseed, and tree nuts. Contamination can occur in field crops, at harvest, or during storage. People can be exposed to it by eating contaminated products, meat or dairy, from animals that have eaten the contaminated feed, or by inhaling dust generated during handling and processing. Even at very low concentrations, such as under 20 parts per billion, it can affect the liver, kidneys, heart, respiratory, nervous, and endocrine systems, and even growth in infants and children. The economic impact is estimated to be over $200 million in total. Conventional methods for detecting aflatoxin contamination include chromatography, such as HPLC spectroscopy and immunochemistry. These techniques are sensitive, but tend to also be cumbersome, requiring a lot of sample preparation and skilled, well-trained operators and expensive equipment. Non-imaging optical methods, such as Raman spectrometry, render averages over large areas or points on individual samples, so they aren't practical for assessing large quantities or product line inspection. Recently, systems have been introduced utilizing UV and blue lasers as excitation sources to stimulate visible fluorescence in various types of aflatoxin, which can be seen with a color camera. Unfortunately, these approaches lack specificity because other components and agents in the samples also fluoresce, leading to high numbers of false positives and ambiguous results. Hyperspectral imaging cameras capture hypercubes or data cubes of data in which the spectrum at each pixel in the image is collected. Using spectral imaging, one can distinguish subtle color differences that are not detectable by eye or regular cameras. These are optical-based systems that can be used in the detection and identification of foodborne contaminants. We've demonstrated its potential with specimen samples extracted during processing, such as poultry rinse or wash water. We envision this technology as part of an inline inspection on the product itself or within the food matrix. There are several different technologies used in hyperspectral imaging. Push booms are the oldest. A grating spectrometer captures a line on the object plane, generates a 2D pattern on an array sensor where the one dimension is that line and the other is the spectra. So to capture an area, you need to mechanically scan that line. The process can be slow and prone to non-uniformities. Band sequential or front-staring imagers don't require that scanning. They use a tunable filter that can sequentially select spectral bands placed in front of the sensor and can collect complete images at each spectral band. The acquisition time does not depend on the number of pixels, but on the number of spectral bands. Multispectral or pattern filtered arrays are basically an extension of color cameras, where instead of RGB filters overlaid on the image sensor, you have an array of 16 or even more color filters mosaicked on them. Spectral resolution is typically quite limited and comes at the expense of spatial resolution. Our systems utilize a Fabry-Perot interferometer, or FPI, in a front-staring configuration, but allowing for multiple bands to be captured per exposure. An FPI acts like a spectral band filter by placing two mirrors parallel to each other, such that the constructive and destructive wave combinations can be used for band selection by varying their spacing. By controlling the reflectivity of the mirrors, we can also set the bandpass resolution also. These devices can be fabricated in a semiconductor process, and the imagers can be made very compact and robust. We can configure it into form factors and configurations suitable for laboratory benchtop investigations, production line testing, and microscopy. This is typically not possible due to cost, speed, reproducibility issues, environmental, and power restrictions of other technologies. In fact, we developed the world's first battery-operated handheld front-staring hyperspectral camera, the 4100. This camera captures multi-megapixel images in 300 spectral bands in as little as 2 seconds. It has embedded hardware which enables real-time processing, so you don't have to manage large data sets it generates, and just set it to identify features of interest and indicate them. Data cubes themselves are not intuitively interpretable, so you have to use mathematical processing or machine learning to identify spectra of interest by their pixels. This basically involves applying algorithms to large matrices of spectral data, which are represented as vectors in an n-dimensional space. Principal component analysis, or PCA, is used to simplify complexity in high-dimensional data while retaining trends and patterns by transforming data into fewer dimensions by projecting that data onto lower dimensions. K-means is an iterative clustering algorithm used to classify data into a specified number of groups by beginning with an initial set of randomly determined cluster centers, and spectral angle mapping compares a given spectra with a known spectra, treating both as vectors and calculating the spectral angle between them and grouping them with respect to a threshold based on that angle. From that, a composite image can then be generated, such as a false color rendering. This then can be easily interpreted to determine the presence of toxins and enable the operator to take immediate action. You could then also apply statistical methods to that data to provide a binary answer, response, go, no-go flags, or warnings, thus automating this inspection. We were presented with samples of finely milled cornmeal infected with aflatoxin concentrations ranging from 0 to over 300 parts per billion. Each sample was distributed evenly in individual containers and placed under a quartz tungsten halogen lamp, and data cubes captured using the Model 4200 Hyperspectral imager. We tried to ensure they were illuminated as evenly as possible. This is a schematic for the relatively simple setup we used in collecting data for the cornmeal aflatoxin samples. Reflectance spectra of samples with low concentrations or of no aflatoxin were compared with higher levels to identify spectral differences. We created spectral reference libraries for classification. We then used a spectral angle mapping algorithm with a null scalar to segment the images. Pixels where the presence of aflatoxin was detected were false colored red. Baseline samples with no contamination false colored green in classified composite images. Here we see samples at 0 on the right in red and 301 parts per billion on the left in green. Similarly, we have 0 parts per billion on the right and 103.4 parts per billion on the left. Note the difference in the spectra is fairly distinct. At 0 and 18 parts per billion, a difference between the spectra can still be easily detected. However, at lower concentrations, it becomes very difficult to tell them apart. Here we see the spectra are very close at 6 parts per billion, and in fact the segmentation shows almost no difference. What differences are seen are within the variation of two samples both at 6 parts per billion. These side-by-side comparisons show clear discrimination between contaminated and uncontaminated samples to aflatoxin concentrations of 0 and just below 18 parts per billion. We don't see any discrimination between 0 and 6 parts per billion. This is of note as levels of 20 parts per billion or greater are typically defined as thresholds for health risk and a basis for action. This means this method potentially has the sensitivity needed to serve as a gauge for product safety. A further series comparison was captured to confirm the sensitivity threshold. Additionally, unsupervised classification yields similar results and does not identify any additional components. Here we see a comparison of 0, 6, 18, and 301 parts per billion. This slide compares 0, 0, 103, and 301 parts per billion. Our unsupervised classification of the previous data involved principal component analysis with 7 components and k-means clustering with 5 clusters. Again, no additional n members were observed from that which was found using spectral angle mapping. We observed that the spectral differences between infected and non-contaminated samples were within 10%, and that the classification performance is dependent on position and height. These influence the degree of surface reflectivity, so the sample distribution should be reasonably even and flat and placed at a sufficient standoff distance and field of view of the imager. So in summary, we have demonstrated the potential for use of hyperspectral imaging technology for measurement and monitoring of aflatoxin levels in cornmeal, which pose a risk to human health. We've shown that high concentrations above 20 parts per billion were easily differentiated, but results become ambiguous below that level, and noted that the differences were evident with both supervised and unsupervised classification. And finally, we learned that the distribution of samples should be reasonably even and flat and placed at a reasonable standoff distance and field of view of the imager to mitigate influences from variations in surface reflectivity. Cornmeal is a processed product. Intact items such as unmilled grains, nuts, and seeds are of significant interest. In such samples, fungal infections can often be quite localized, appearing on one side of the product and within a small area. There is also often great variation in contamination. To assess these types of products, one needs to independently determine concentration and coverage of aflatoxin to use as ground truth or reference. Because of the many significant sources of spectral reflectance are of the same orders of magnitude as the spectral differences between contaminated and uncontaminated samples, new discriminative multiple instance target characterization algorithms, such as multiple instance adaptive cosine estimators and spectral matching filters, have been applied to this problem by our colleagues at the University of Florida. These identify discriminatory spectral signatures rather than actual reflectance spectra and are based on training data which contain instances of target information known as positive bags and non-target information called negative bags. This approach enables classification from images based on subpixel information where pixels may not contain pure spectra, but a composite. These are example spectral signatures of aflatoxin contaminated peanut pods. And these are classified hyperspectral images of those peanut pods, captured with the model 4200 and classified using the MT-MIACE algorithm to detect aflatoxin from those target spectra. We'd like to thank our collaborators Diane Rowland and Alina Zaire at the University of Florida and our industrial partners at Neogen Corporation for their assistance in providing the aflatoxin cornmeal samples. Thanks for listening. We're happy to answer any questions you might have.